All right, so I'm going to be talking about... That's great, thank you. I'm going to be talking about astrophysics simulations, and hopefully we have a better reason for doing these than the cartoon might suggest. I'll let you read the caption. Many examples, cosmology, study of globular clusters, tidal disruption when a star goes by a black hole and gets torn apart, accretion disk, planet formation, and so on. Perhaps the most famous recent example is the, you'll see from 1509-14, that's the date of the first gravitational wave detection by LIGO. And this is the famous figure from the discovery paper. And on the top, you see these are the waveforms from the two detectors, Hanford and Livingston. And on the bottom, the waveforms again slightly broadened to show the uncertainty in the reconstruction. And then superposed on top is the waveform that comes from a direct numerical solution of the full Einstein's equations of general relativity, no approximations. Okay, and then you can just see by eye, you don't have to do any fancy statistics. You can see what a good match that is. And in fact, that's how we can say with confidence, right? We know with confidence that the experiment detected gravitational waves. But this matched is what tells us that the waves came from two big black holes and tells us the masses of the black holes and so on. And this particular waveform was done by our collaboration. SXS stands for Simulating Extreme Spacetimes. In fact, there's a local connection to that because this particular code that I'm going to mention several times was developed originally at Cornell. The three original authors of that code, one of them was Harold Pfeiffer, who was a faculty member here, who was a graduate student at Cornell at this time. Okay. The history of this numerical relativity project is actually quite interesting. This is the first paper on the subject. You'll see 1964, right? So over 50 years ago. And in modern language, what we would say is they were attempting to simulate the head-on collision of two black holes, right? So by doing an axisymmetric situation, it's a little easier numerically. And there are some quaint features, right? They did 50 time steps. Today, we do many tens of thousands. This took 3 CPU hours on an IBM 7090. Here's the mesh size they used, and they integrated for this is like 1.8 light crossing times. I mean, a very short in. What's interesting is the conclusion of the paper. In summary, the numerical solution of the Einstein field equations presents no insurmountable difficulties. Now, when you read the paper carefully, you'll find the reason that they stopped the simulation at this time was that their code blew up. But anyway, it wasn't actually until 2005 that this problem of codes blowing up was finally dealt with satisfactorily. So the focus of this talk is going to be on partial differential equations, right? Lots of important problems, especially in astrophysics, but in many areas. So hydrodynamics, magnetohydrodynamics, gravity, whether it's Poisson's equation for Newtonian gravity or Einstein's field equations, some ways of treating radiation transport. These are all PDEs. So I'm not concerned with n-body things, so you have a bunch of particles and you directly integrate their trajectories by computing the forces between them, or Monte Carlo. And the reason for this distinction, as you'll see, is related to how you can parallelize the codes, how you can take advantage of solving a large problem in a reasonable time by making use of many processors on a big supercomputer. And so the point is that if you're doing n-body or Monte Carlo, it's trivial to parallelize because every particle's trajectory is independent. You can just take a little time step and then you compute forces. Monte Carlo, by definition, you're sampling. And so you can just, start a new sample and then another one and another one and another one. So there's no crosstalk. But with PDEs, you have to take a derivative. And fundamentally, a derivative means you need a function value here and a function value here, and you take the difference and divide by delta x. And that's how you approximate a derivative. And no matter how the numerical analysts dress it up with making it all fancy, you can't get around the fact that you need function values at 2 points. And if this point lives on this processor and this point lives on that processor, then they have to communicate in order to take the derivative. And that causes all kinds of problems, right? So that's going to be at the root of this. All right, so this is the dirty secret that for the past 50 years, if you look at the numerical methods, for example, that were in that 1964 paper, and you look at the numerical methods, by and large, that are used today, essentially nothing has changed. Okay? The root of it is finite differencing. You want to evaluate a derivative, you take a difference and divide by delta x. So all that has improved is we can use smaller delta x's because we have bigger computers with more memory. Right? But fundamentally, this is what's been going on. So one thing that distinguishes this code is called Spectral Einstein code. There are about 10 groups around the world that can solve Einstein's equations the way that I've described earlier. 9 of them use finite differencing, but the SXS code, spec, uses something called spectral methods. So let me explain, I'm going to explain what that is and why it's a good idea. So the point is that when you're solving Einstein's equations, it's purely gravity. You don't have any other forces or fields in the problem. And the solutions are smooth, except if you get near a singularity. So that suggests that you should use higher order methods. Right? When you approximate a derivative by just taking a difference between 2 neighboring points dividing by delta x, that's a crude approximation to the first term in a Taylor series expansion of the function about a point. But you could imagine using more points to get a better approximation to the derivative. So for example, here are a bunch of grid points, and suppose you want the derivative at this point. You can work out using Taylor series a formula where you might use, say, these 5 points to approximate the derivative here. And that works fine. You can get higher order approximations. But the problem comes when you get to the boundary. At the boundary, you can't center the approximation nicely. You can only use one side. And what you find is that's unstable. As you add more and more points to get a higher order method, the coefficients in that approximation get bigger and bigger and alternate in sign. So you're approximating some number by the difference of 2 very big numbers. And that's not a very good thing to be doing on a computer. Right? You lose accuracy. So this is what prevents ordinary finite differencing from being successful when you try to go to high order to do better than just doing a simple approximation to a derivative. The point about a spectral method is, in one sense, all you do is you use a non-uniform grid. And by carefully choosing how these points are distributed, it turns out you can approximate the derivative anywhere on your grid by using all of these points to get a very high order approximation to the derivative. Now, there's another way of thinking about this. You can think of this alternatively as approximating a solution as a superposition of some basis functions. So this is exactly the same kind of thing when you solve problems by separation of variables, when you have your graduate course in E&M or in quantum mechanics, right, where you do things as a superposition of basis functions. So the only difference is because it's a computer, the sum doesn't go to infinity, it's a truncated sum. So in a true spectral method, the way you get these coefficients here, so these are the basis functions in x, these are the coefficients, right, is you use the orthogonality of the basis functions to get an expression for these spectral coefficients. And what turns this into a useful numerical method is instead of doing this as an integral, you do this as a Gaussian quadrature, right? So it's a finite representation, a finite approximation to the integral, right, by some carefully chosen weights and then some collocation points, positions x sub n on a grid where you evaluate the function. So in fact, if you think again to quantum mechanics, if the basis functions you're using were e to the ikx, just a Fourier series, then this is like representing a function either in momentum space, right, because here you have it, these would be e to the ikx, and then these would be the amplitudes of each momentum space basis function. Alternatively, you can represent the function in coordinate space, the f of x n's, right? They're at the grid points. So it's just a transformation between spectral space or momentum space and position space. So the nice thing is now you have an alternative way of taking a derivative. You don't have to take the difference between 2 points. You can take a derivative of an expansion like this by just differentiating the basis function, which you can do analytically once and for all. Okay? And so that's the sort of the new wrinkle to this. The payoff for this is if the function that you are expanding in basis functions is smooth, you get exponential convergence. That means as you increase n, the approximation to the true solution, that error gets smaller and smaller faster than any polynomial, right? It's an exponential convergence in n. And so that's why for solving smooth problems, the spectral methods are basically the most efficient method that you can imagine doing. And this is why this spectral code that we've been using for Einstein's equations has been so successful. However, you don't get anything for free. If you want to do a problem that's not smooth, so in particular you want to smash 2 neutron stars together, I can't imagine why you might want to do that, but right, and see, calculate what happens. Now you get shock waves, and as you know, for example, if you try to represent a discontinuity by Fourier series, you get Gibbs phenomenon. Well, that's a general feature of these expansions in basis functions. You get Gibbs phenomenon, and so you lose, not only that you lose the exponential convergence, but even at low order, it's not very accurate. All right, so what to do? All right, so since I already mentioned this, right, if you want to include matter, for example, in my case, I'm interested in doing simulations of binary systems with black holes and neutron stars or 2 neutron stars, right? So here's the famous figure that appeared on Monday in PRL. Right, at the bottom is so this is time and this is frequency. And so this is the gravitational wave strain in LIGO. And so the color shows the amplitude of the waveform getting larger and larger, and then the frequency going up in time. So this is a chirp signal, which is characteristic of a binary merger. And then, so this is the time of merger, and then these are showing counts from, this is the Fermi gamma ray burst monitor at low energies and at higher energies. And this is integral, which is another gamma ray satellite that detected this event. And you see about 1.7 seconds after the merger, there's a short gamma ray burst, and 75 papers appeared in various journals on Monday. Okay, so suppose you want to model the physics that goes into this, right? So you want to be able to start with two neutron stars, have them being orbiting, radiate gravitational waves, spiral together, smash together, make some kind of a hot remnant, maybe some matter gets ejected and makes gold and platinum or whatever it's supposed to do, and gamma ray bursts and kilonovas and all this kind, right? This is a challenge to be able to model this. So we can't do that yet. We can't actually go from the beginning to the end. We can do little pieces, but can't put it all together. All right, and you have to do this all in full general relativity, of course. So this is a slide that I've been using actually for a little while to illustrate this sort of grand dream of detecting some event. So this is supposed to be a black hole that's torn apart an in-spiraling neutron star. And then we would hopefully detect gamma rays, light, gravitational waves, maybe even neutrinos from this. And this is called multi-messenger astronomy. Well, multi-messenger astronomy is here, right? This is an incomprehensible figure that appeared in the multi-messenger paper. But you're not supposed to follow the details. I'm sure you can't read even what's there. But this is supposed to give you a sense. So here is the detection in gravitational waves. Here's the detection in gamma rays. So that's shown. So this is sort of different. This is gravitational waves, gamma rays. This is time in seconds. So you'll see that's the scale for these things. Then here the scale switches to days. And these little tick marks are the times at which various circulars were sent around by all the observers reporting on their different observations. And some of them were actually just reporting that they'd seen nothing, right? But everyone was looking. And so, you know, this is X-rays, ultraviolet, optical, infrared, radio. And by now, this event has been seen in all of these bands. So here's the original identification of the optical counterpart. This is Chandra X-rays. This is the VLA showing the radio detection and so on. So this is a real thing as of Monday, right? And the paper from which this figure is taken has 3,500 co-authors. Okay, I think it's more than a quarter of all professional astronomers in the world were involved in this. Okay. All right, so let's go back to the problem of simulating this, right? So for the experts in the audience, I've got some of the buzzwords here describing the ingredients of our particular code, and I'm not going to go into that, right? So this is, again, a black hole neutron star simulation. The important point is the accuracy, or rather the lack of accuracy. So the gravitational wave phase for this particular one is about 1 radian of error after about 10 orbits of in-spiral. And we actually do a little bit better. Our most recent thing is about a 1/10 of a radian over 20 orbits, but it's roughly that. So the error in the in the black hole and the geometry and so around here is about 1%. The error in the matter here is bigger, maybe 10 to 50%. That's not good enough, even for astrophysics. Okay? I'll explain that in a minute. But first, let me show you this little movie. Just since it's a computational talk, I have to show a movie. All right, so here you'll see, in this case, the black hole has some spin, so you'll see this sort of precession effect and then things being torn apart. And this background grid is our computational grid covering the matter. And then you see a nice accretion disk formed in the end, and who knows, maybe a jet gets launched, something like that. Okay. So the problem comes not just from being able to do these calculations, but if you look ahead to how the experiment is going to improve. So let's first look at black hole, the pure binary black hole case. So When LIGO reaches its design sensitivity, hopefully in about 3 years or so, the signal to noise will improve by about a factor of 3. So that means you will be able to see events. Remember, gravitational wave detectors are sensitive to amplitude, not to intensity, like electromagnetic spectra. So amplitude falls as 1 over r, not 1 over r squared. So if you increase your sensitivity by a factor of 3, you can see events 3 times further away. That's 27 in volume. Okay, so your event rate should go up by 27. So instead of 1 a month, you'll see 1 a day. The signal to noise of the loudest events so far are like 25, 30, something like that. So we can expect to be seeing events, some of them at least, with signal to noise, right? The same event will be 3 times stronger if your sensitivity improves by a factor of 3. High signal to noise, that means you need a phase accuracy over the in-spiral, which is about 1 over 100. Okay, so very high accuracy. And then if you extrapolate after that, over the next 10 years, as long as the NSF keeps the funding going, another factor of 4, 4 cubed is another 64, right? You can see it's not that we'll want to simulate every detection numerically, but we will want to simulate some of them, and some of them we'll want to do to very high accuracy, right? If you want to say, is general relativity really the correct theory of gravity, or is some, crazy string theory inspired thing in the low energy limit, predicting some scalar waves or something like that, that's some modification of general relativity, well, we'll be able to tell. Every little wiggle in that waveform will be significant. And so we need to be able to do calculations to much higher precision than we can do today. And if you look ahead to LISA is a proposed gravitational wave detector in space that will be sensitive to events from supermassive black holes of 1 million solar masses. That will have extremely high signal to noise for some events, right? So the accuracy challenges, if you look to the future, are very high. For neutron star codes, right, as I said, the computational errors are much larger because you can't use spectral methods. In fact, you can't even quantify the errors because we always report our results. Right? The way you quantify the error is you run at different resolutions, right? The size of your delta x, and then from that you can try to infer what the error is. But the problem is you always report the results for your highest resolution run, so you can't do another higher resolution one to kind of figure out what the error is. So, it's a difficult problem, and the simulations take too long, right? I mean, most of these, if you want to simulate 20 orbits of a binary neutron star merger, typical codes take 2 months running on big supercomputers. The most important problem, though, is this problem is not going to be solved by just letting computers get more powerful. So if we look at what computers will be like 5 years from now, the main difference is that they will, instead of having thousands of processors, they're going to have millions of processors. And what I want to explain is why you can't just take today's code and put it on a machine with 1 million processors and get anything useful out of it. Okay? But first, let me explain what's wrong with 1% accuracy, right? I mean, as I said, it's astrophysics. Right? So there are many examples. For example, you have a black hole that tears apart a neutron star and forms the accretion disk. And then you want to study what happens to the accretion disk. So typically, about 1% of the original mass ends up in the accretion disk. Well, if your accuracy of your simulation is 1%, then the error in the properties of that accretion disk is about 100%. Right? It's it's not quite as bad as that, but you get the idea that if you want to say something about a small piece of a system, you need a much higher overall accuracy than you might have expected. So core collapse supernovae, right? So you all know that the supernova problem, right? How does a collapsing star end up exploding and making a supernova? That's been an unsolved problem for 50 years. And the reason that problem is so difficult is that you start with an initial configuration where the potential energy in the star and the thermal energy in the star are sort of in balance. So the potential energy is negative, the thermal energy is positive, and they're adding up to approximately 0. And then, as the collapse proceeds, some of that potential energy gets more negative, right? It's getting more tightly bound, and you get kinetic energy that balances, but the total energy still adds up to 0. So you're balancing two very big numbers, and you have to track that difference then to better than 1%. And that's why it's just hard. You have to get everything right to that level of accuracy. Those of you who looked at the paper that came out, the discovery paper that came out on Monday, there was a plot of the tidal effects, right? The way you can tell that it's two neutron stars and not two black holes, say, that are orbiting together. One way is because astrophysicists tell us you can't make small black holes. I mean, there's no reason in general relativity why you can't do it, but we don't know any good ways of making small black holes. On the other hand, typical neutron star masses are the masses that we're seeing there. So we shrug our shoulders and say, well, must be neutron stars, right? But you could tell for sure because neutron stars will induce a tidal deformation on each other as they get close. So you raise a quadrupole bulge on each neutron star, and the interaction of those tidal bulges drains some extra energy from the orbit, and so that accelerates the merger, and you can tell the difference between neutron stars merging and black holes merging if you can measure this effect. All right, so let's suppose that LIGO, it's a marginal kind of measurement in the first detection because we're probably going to have to wait till LIGO gets to design sensitivity to do this thing reliably. But the problem is you have to be able to model this accurately enough to see the small little bulge that gets induced as these things get close together. And you have to believe you've done that accurately enough. Okay, so you need to be able to do these things. And then there are problems where you just get completely the wrong answer at the sort of the 1% resolution error. So for example, there's a thing called the magnetorotational instability that can went from magnetic fields that form in accretion disks. And this is an instability where if your resolution is too coarse, you don't see the instability at all. It's a small-scale instability, so the resolution of your code has to be fine enough before it shows up. And if you omit this, you're just not modeling the system accurately at all. So there are lots of kinds of problems where you need this thing, and I've been focusing mainly on the problems which are driven by looking at the increased sensitivity of LIGO, but there are other areas as well where this comes up. So why is it so hard? Well, there are all kinds of, you've got surfaces, shocks, multiple time scales, the geometry changes, multi-physics, right? It's a complicated problem. So how are we going to do this? Okay, and the answer is an algorithm called discontinuous Galerkin methods, right? So I'm going to explain what that is. At least I have the humility to put a question mark there, right? So this is what I believe is one way to handle all of these complicated kinds of things. So let me explain what this is. All right, so finite volume methods, which is a fancy name for finite differencing, So you can think of these in the following way. Here I've divided up my grid into 3 cells, right? So imagine a grid point at the center of each of these cells. So what you're doing, crudely speaking, is you're representing the solution just by the average value of the solution in each cell. Okay? Now, the cells are connected because typically you're solving a conservation law, like the equations of hydrodynamics just say that momentum and energy are locally conserved. So any momentum or energy that's leaving this cell must show up in this cell or the one to the left. So the art of this kind of method is how you describe the fluxes that connect the cells. But people have had a lot of time to work on this. There's a lot of good ways of doing that. And these flux reconstruction methods can handle shocks. The problem is when the solution is smooth, you would like to use higher order methods. So the only way to make a method higher order is you have to use the information from this grid point, this one, and this one. You're coupling together many cells. Right? And that gets you into the problem not just of communicating with your neighbor, but with your neighbor's neighbor and right, further and further away. And as soon as you put that on 1 million processors, you're dead. Right? You spend all your time waiting for information to come and no time actually calculating things. Now, the spectral code, right, as we said, you expand the solution in each little subdomain as a superposition of basis functions. Here I've shown just 2, right? Here's a constant plus linear in x. So you can imagine an x squared and an x cubed and higher order polynomials that you're using. Right? So, so here's the solution in green, and then since I'm only using 2 basis functions, right, it's being approximated by a straight line in each cell. Right? So you get exponential convergence in smooth regions, but the fluxes for the spectral code can't handle shocks because of the Gibbs phenomenon. So a DG code tries to combine these 2 ideas. So basically what you're doing is locally you expand the solution in a basis, just like spectral methods. But the way that the fluxes are done allows you to use arbitrary in quotes, but pretty arbitrary, so you can handle shocks. Okay, so the art again is in how you connect the regions to each other. All right, so let me just explain that briefly. All right, so you have some conservation law. You expand in basis functions. So you substitute these expansions in here. All right, let's take S over to the left-hand side. So we want that to be 0. But we can't get it exactly 0 because we're using an approximation. We're only using n basis functions. So the way Mr. Galerkin got famous was he said, well, the best you can do is if the inner product of the residual against the set of basis functions I'm using is 0, right? So this is the residual, and these are this spans the set of functions that you're expanding in. That's the best you can do in some mathematical sense of what you mean by best, okay? Okay, so if you look at this equation, there's a term here, this divergence of the flux, again, in a product with a basis function. All right, so you have this quantity, right, and who can see what I should do next, how I should rearrange that term? Right. So the way you can tell the difference between an experimentalist and a theorist is a theorist knows that whenever you're stuck, you integrate by parts. So anyone who's an experimentalist and wants to switch, you now know what you need to know. Okay. So you integrate by parts, And then you get a total divergence, and you convert that with Gauss's theorem into a flux integral. Now, we're still doing this in a subdomain, and then the way you couple the subdomains is you replace this flux at the surface by a numerical flux. So this is something which is an approximation to this that uses the information from both sides. Okay? And so that's where the art comes in. And it turns out that this method, which was developed for mainly for terrestrial fluid dynamics applications, you can actually generalize this. All goes through in Einstein's theory, and you can take it over to do relativistic things with it. Okay, so here's a little test problem that was done by my graduate student. It's a standard test problem where you have a relativistic inflow here and here. I can't remember, something like Mach number 10 or something like that. You have an initial condition, which is a high density gas over here, and then low density here, and then you form this very intricate pattern of shocks and contact discontinuities, and then you can compare this to standard codes that do this, and it can resolve all of this and no Gibbs phenomenon, and everything handles it. Okay, so we're building a new code, which we're calling Spector, to do this. So to implement this DG method, and to be able to run it on machines with 1 million processors. Okay, so how are we going to do that? So the problem is that Moore's law actually is broken. Okay, I don't know if you all knew that, but Moore's law says basically that every 18 months or 2 years or whatever, the speed of processors doubles. Okay, and that's not true anymore. And the reason is that basically the size of the wires, if you like, that connect all the components on the chip are now down to something like 70 atoms. There just isn't a heck of a lot of room left to go much smaller than that. So the way that the next generation of machines, and you can already see it when you buy laptops today, the way that the power of the machines, you see, they don't tell you what they mean by power. The way that the power keeps increasing is they put more and more chips, more and more processors on a chip. So here, this is from the IBM Blue Gene. So this is actually this is 2 generations old in supercomputers, but it's the one which I had the nicest picture of. So this is, 3/4 of an inch square. It's about that big. And those of you in the front row might be able to see the labels here. This is PU, processor unit 00. So this is number 0. And then going around here, you can see PU all the way up to 17. So actually, it turns out that one of them is for oversight and so on, and then they use 16 of the processors are actually used, and then one of them gets disabled. And the reason for that is when they make the chips, they don't get perfect chips. So they make an extra, it's cheaper to make an extra CPU, and then if one of them is broken, they just disable it, and then they have the 16 they can use. Okay, and then what's happening is basically this 16 is now 32 or 64, and this is going to rapidly increase. And then you stack many thousands of these chips together, and you get supercomputers that currently maybe have tens of thousands of processors, but then will soon have millions of processors. So the problem is, if you take current codes, there are 2 problems, right? One is this communication problem, right, with the finite volume code. If you're not using DG, you have to communicate not just to neighbors, but even further afield, where the solution is smooth and you want to use high order. the processors then are idle. They're waiting to get data before they can do their communication. And then also you have what's called a load balancing problem. You might have one processor which is somewhere in a neutron star where there's some local physics that you have to calculate. And then you might have another processor that's out in the wave zone. It's just got some boring gravitational wave that's coming by, no complicated nuclear physics. So it finishes its calculation very quickly, and then it sits there waiting until this one finishes so that you can now take the next time step. So the solution to this is to give up the way that we're currently parallelizing and to switch to a new mode, which is called task-based parallelism. All right, so let me just illustrate that. At the top, so like in existing codes, like our spec code, so you have a bunch of tasks, each one running on a different processor. And so this is the time it takes to finish this task, and then the processor waits until the slowest guy finishes, and then you can now start another time step, say, at this time. In task-based parallelism, you have a whole bunch of tasks that you line up on your master processor, and then you have a bunch of slave processors, and then as one task finishes, a new one gets popped off the queue, and you start executing it. So the idea is you never have idle processes sitting around. Right? If a process is waiting for data to be communicated, it finds something else useful to do in the meantime. Okay, so the problem with this, why isn't this why? I mean, it seems such an obvious idea. Why isn't this widely adopted? The reason is there aren't good software packages that let you do this. Okay, and the one thing that you should remember as a physicist is never write something that a computer scientist could write for you. Okay, you will take 3 times as long and probably not do as good a job, right? So the problem is that there are not many good packages, but we found one. And it's called Charm++. And if you're interested in this, I would recommend that this is the thing that you look in. Right now, all the computer science-y things that are out there are so bleeding edge that they're not useful. You can't do anything with them. So here's an example from our Spector code. So this is a standard test problem in magnetohydrodynamics. We ran it actually with a relativistic MHD code just because that's what we wanted to benchmark. And so the Blue Waters machine is a machine that has approximately 600,000 processors that you can't routinely use, but if you make a special request when they take the machine down for maintenance, then when they bring it up again, they'll give you 10 minutes before they let everybody else on the machine, and you can have the whole machine. Okay. So here we took a big enough problem that at every size of the number of processors, right, it would basically fill even at the biggest number of processors would fill the machine. And you can see that as we increase the number of processors solving a fixed problem, right, every time we double the number of processors, the code ran twice as fast, finished in half the time. And that's the ideal situation. That means that typically when you do this, if you took a standard code and try to do this, what you find is it scales very well for a while, and then this flattens out. Adding more processors doesn't help you because you're stuck by the communication that's coming in. But the real impressive thing about this is we took the code from a laptop and put it on the supercomputer, made 0 changes to the code, and got these results. Right? Typically, there are people who are experts in finite difference codes who can get sort of results like this for specially tuned problems. They spend many, many person months tuning their code to a particular machine to get this kind of performance. But by going to task-based parallelism, the human time is greatly reduced. Right? So this is the future. And here's just another interesting way to see it. This is a time profile, just 10 time steps of that previous test. So the way to understand, this is time along here. And this is, the different colors are different tasks that are in the algorithm. That, so the sending data from one cell to the neighbors, computing the divergence terms in the volume, all these kinds of things. So that's what the colors are. So the white is when the machine is idle. The processes are doing nothing. So at the beginning, you have to start up. That's this blue setting things up. And there's some white because you start just on a small number of processes. And then once things get going, you can see you settle down where there's no white. There's something useful being done at every time step. The black here is the overhead of the charm++ that's sort of managing everything, and that's about 10%, so you can live with that. And then at the end, as you wind down, right, there are fewer and fewer tasks to be done, so you can see gradually more and more white here. All right, so this is very good. But this is test problems. We haven't demonstrated this yet for a real binary neutron star merger or something like that. All right, so there's some challenges. I'm going to skip over this local time. Well, maybe I'll just mention. One of the problems in these big codes is the resolution requirements are different in different parts of the domain. So for example, if you're simulating a small black hole that's going to merge with a big black hole, the resolution that you need in your grid now around the small black hole is much finer than the resolution around the big black hole, right? It just has smaller length scales on which things change. And when you do time stepping, the time step that you can use is set by, it's controlled by what's called the Courant limit, which is basically proportional to the size of the spatial mesh. The smaller the spatial mesh, the smaller the time step that you can take. So what you would like to do is take different time steps in different regions, right, which is easier to do if you've got task-based parallelism, whereas if you don't have that, it's very hard. It doesn't help you to take small time steps over here because the processes responsible for this part of the mesh just sit there idly doing nothing. So you do 10 time steps over here, and then this one says, oops, I better take a nice big time step. Okay? But you don't buy anything. So another tip for you, those of you who write proposals for computer time, the allocations committee always asks you to present a scaling plot, right? One of those plots that I just showed earlier, of how well your code does as you increase the number of processes. They want to see the speed up. And they want this because they want to be assured that you're using their big machine efficiently. Well, what should you do if you have a code with different mesh sizes and so on? What you do is you choose a step size which is appropriate for the smallest mesh, and then you take that time step everywhere. So it's wasteful on the big zones, but, right, you'll get perfect scaling now, okay? Even though you're only using 10% of the machine. All right, so remember that one, okay? So in fact, this is a known kind of thing. So let me summarize what my punchline is. So we've had 50 years, finite differencing has had a good run, but it's time we really need, we're physicists, we tend to get kind of lucked. We found one good way of doing things, we don't open our minds. We really are going to be forced to do this by the new generation of machines. And we should be open to new algorithms like this DG method, which are high order, which is good for efficient for smooth solutions, but can handle shocks. They're local, so you get good scaling. And task-based parallelism is an idea that can be used in many, many kinds of computer codes. And you should really think about that if you're doing a big problem. Thank you.